Okay, welcome Earth Science 11 to the first of two videos we're going to do this week, looking at the relationships between temperature, pressure, density, and humidity. So the plan is, for the first video, we are going to look at how temperature varies throughout the day and throughout the year and why, and we're going to look at humidity and how it can change the way that we feel about the temperature. In the next video, we'll cover these two topics, understanding density and how it relates to temperature and pressure, and then understanding air pressure and how it helps to determine the weather. So, let's get started. Now, all of the information I'm going to share with you is information that you will need to answer the questions that are on the accompanying worksheet. So, the first section of the worksheet is temperature, and that's what this is all about here. So, if you recall, if you were in class earlier this year, we did this graph where we looked at the temperature as we launched our weather balloon into the atmosphere. And hopefully you can just take a quick look at this and see the relationship between temperature and altitude. So as we go higher and higher and higher in the troposphere, the temperature is going to get lower and lower and lower. Now, we also saw that the temperature changes, it increases again once we get past the troposphere, but considering that we're talking just about weather, and all of the weather happens in the troposphere, then that is enough for us to worry about now. So, how does temperature change with the time, and why is that? So throughout the year, obviously temperatures are higher in the summer months and lower in the winter months. That's not a surprise to anyone. The reason for this is just based on how many hours of daylight you receive a day. So this is a graph that shows essentially the sunlight hours throughout the year. So in January, it's sunny at around 8 o'clock and finishes around 4:15, 4:30, something like that. That's the time that is considered the day. All these darker areas here are nighttime. So you can see during the summer, June 21st being the longest day, we can see here that there's a lot more sunlight. If we're getting more sunlight, and also the sunlight's more direct, then we're obviously going to have much higher temperatures. So more energy is being added to the atmosphere, and we're going to get higher temperatures as a result of that. Okay. What about throughout the day? So on the right-hand side here, I've got these two graphs. One of them is from San Francisco, which many of you know, I'm sure, is right next to the coast. So it's right next to the ocean, beautiful seaside city. And then we've got Yuma, Arizona. Now, Arizona is far from the coast. It's a landlocked state, or at least Yuma is not anywhere near the ocean. Now, these graphs have something in common, and they also have something that's quite different about them. So what they have in common is that during the day, so you can see this line here, this line here, this line here, these are all essentially around noon, and these lines here, the ones that are in between the numbers, these are midnight. So this should come as a surprise to nobody. During the night, the temperatures are quite low, and during the day, the temperatures are quite a bit higher, and that goes the same for every day. Lower, higher at noon, lower at midnight, higher at noon, etc., and that carries on. So this is what they both have in common. They're hotter in the afternoon than they are at night. And that, again, is to do with the fact that they're receiving that sunlight during the day and heating up, and then they're radiating that heat back out to space during the night. So they're getting colder and colder. But if you look at the size of the temperature change in Arizona, it's huge. It goes from, if we're looking in Celsius, somewhere around almost 40 degrees down to about 20 degrees at night if we're looking at, the 7th of the month, whatever day this is here. So a massive temperature difference, and then over here it's a very, very small difference. So the difference is from 20 to maybe 17 or 18. So only a couple of degrees difference. So why is that? You've probably noticed this yourself if you've ever gone to the beach on a really hot summer day and that sand is just burning your feet and you're just doing a little hop, jump, run as to get down to the water as soon as you can to prevent your feet from getting burnt off. And the reason why that happens is because water is able to store way more energy than dirt, plants, or land. So there's a couple of reasons for this. One of them is that as the sunlight hits the surface, it's really only touching the top layer of surface. So it's only that top layer of soil or sand or whatever it is that's getting that direct heat, and all of that energy is kind of staying in that top layer. So it's really compressed. All that energy is sort of put into a very small volume. Whereas when the sun hits the ocean, that sun can penetrate a lot further. So instead of just heating maybe the top centimeter of water, it's going to heat all of the water. So that's part of the reason. The other part of the reason is just to do with how it stores energy. So water can store a huge amount of energy without changing its temperature all that much. And so even though if you're at the beach, you've given the same amount of sunlight to the sand and to the ocean right next to it, the brightness of the sun hasn't changed in those two locations. But yet the temperature of the water may only go up by a couple of degrees, whereas the sand may go up by 10, 15, 20 degrees and burn your feet. So this is what the effect of water is on the temperature. So essentially, if you live near a large body of water, like in Vancouver, for example, or San Francisco, because the water is so much cooler than the land during the day, it's going to cool the land down. So you're going to get these sea breezes that take this cooler ocean air and push it over the land to keep things a bit cooler. And then during the night, well, all of a sudden that temperature of the beach will drop way lower, and the temperature of the water will only drop by 2 degrees. So now we're looking at a situation where the temperature of the water is warmer than the temperature of the land. It's warmer than the temperature of the land, and so you're going to get warm ocean breezes that push out over the city. The water is now warmer than the land, so it's going to share that heat. And so the water is going to cool you down during the day, and it's going to heat you up a little bit during the night. So that's why your temperature won't change that much when you live near the coast. Okay, what about humidity? So we dealt with this when we were dealing with the hydrology unit. So we went through the hydrological cycle. Now it's all old information for us, so I'm not going to go over too much detail on it, but it is the way that water moves from the land and ocean to the atmosphere and back in the form of precipitation. So how it goes up in the atmosphere and how it goes back down to the earth, underwater, over water, in plants, etc. So what we're mainly concerned in this unit to deal with weather is just how it enters the atmosphere. That's what we're wondering here, that's what we're focused on here, is it's the water that's in the atmosphere that's really going to affect our weather. The water that's underground is obviously not going to have as big of an impact on the overall weather. And these are two different definitions. We've seen these before. So relative humidity is the amount of water vapor in the air compared to the maximum amount. So we had the example earlier in the year where we had, for example, this jar could hold 8, but only 4 of them are in here. So let's say in this parcel of air we could be holding 8 water molecules, but instead we're only holding 4 water molecules. So this has a relative humidity of 50%, whereas if you have all 8 out of 8, so if you have all the water that you can possibly store in here, this would be 100% relative humidity, and this is known as being saturated. So saturated means it's absolutely as full as you possibly can be. Now another term we didn't focus on as much is specific humidity. So specific humidity is the total amount of water held in the air. So it's not going to be a percentage, it's going to be some value. Like let's say there is 10 grams for every cubic meter. So there's a certain amount of water that's actually in the air at any given time, and this is a direct measurement, not a percentage like with relative humidity. So how does that affect the temperature? Well, it doesn't really have a direct relationship that's very strong between humidity and temperature, but there is a strong relationship between the humidity and how we feel about the temperature. So this should say hot air. So because hot air can hold more water vapor, hot days can have a higher specific humidity. So remember I said that if the air is hot, instead of being able to hold 8, now you can maybe hold 16 water molecules. So it increases the total amount that you're able to hold. So when you have a very hot day, it's like letting a sponge stretch itself out. You can store a lot more water in there. And so when you're out in a hot climate, on a hot day, then on a day that's very humid, you're going to have just a huge amount of water vapor in the air. And so that can make you feel really sweaty. So I was in Shanghai one year, it was like 45 degrees and so humid. And honestly, the moment you walk out of the door, your body is just covered in a layer of sweat. The second you hit the outside, all that water vapor in the air just condenses on your skin and you feel really, really gross. Now, unfortunately, this really has a negative effect on how you're able to cool yourself. So sweating is your body's way of cooling itself down. When we sweat, some of that sweat is going to evaporate. And essentially it takes energy, those molecules, those water molecules that evaporate, they need energy to do that. So they're taking, as long as you're sweating and evaporating, all of that energy that's required to evaporate the water is being kind of stolen from your skin, and that's what cools you down. Now, when hot air is saturated, that means it's holding 100% of the water that it can. You can still sweat, but your sweat can evaporate. Remember that this, if you're on a hot day and it's relatively humid, then you have as much water vapor in the air as you can possibly hold. There is no more water that can evaporate because that water has no space. So the water that's on your skin, or the sweat that's on your skin, it can no longer evaporate. And so you're no longer able to cool yourself down. If it wasn't so humid, then some of your water could leave and go into the atmosphere, but because the atmosphere is already as full as it can be, there's no room for any more water, you can't effectively evaporate. So your sweat just stays on your skin, again, leading to overheating and leading to you feeling a bit disgusting. So that is it for the first video. We're going to cover density next. So you can go ahead and answer the first 2 sections worth of questions now and come back when you're ready to watch video number 2.